Did Sean show up? Scribbling? Okay. Here's this homework back to you from a long time ago. And what I'd like to do today is I think 2 class sessions ago, we'd started working problems with work and energy. Work equals the change in kinetic energy, U equals delta T. And there was a problem that we did number 116 in class, and right at the end of class I was rushing because I got the signal that we were just about out of tape time for the DVD, and I failed to draw a free body diagram, and we were left with a question mark about the displacement of the total displacement of a spring. So what I want to do is go back and clear up that error in that work and make sure you're real clear on how important that free body diagram is. Then what we'll do today is we're gonna start working our problems using energy where we have the work done by active forces other than gravity or other than springs are included in the work function over here on the left side, and over on the right side that sum of that energy or work is going to be equal to the change in the kinetic energy, or that energy of motion, plus the change in gravitational potential, plus the change in elastic or spring energy. So we want to work problems out, and this is the way that I actually prefer to tackle these problems, is to separate it like this rather than the way we had in the previous section. So let's go back to that problem in the textbook. And if you look up on the projection screen here, you can see that problem. And what we had before, and we'll redraw it, and then I'll just write up a proper free body diagram, is we had this 2 kilogram mass that slides down this smooth rod. No, excuse me, there is friction. 0.4 is our kinetic friction coefficient, and it slides down that rod with friction. And then we computed the correct velocity when it first touches the spring. We did that previously. Then once the spring starts acting, it's doing work. That spring's doing work against the mass. And then that's going to cause it to slow down and eventually come to stop as the spring goes into compression. Okay? So let's get that correction taken care of. And so I'll just redraw the free body diagram up here. And if you're watching that old DVD from a couple days ago, back on the 28th of April, I think it was, then what I did is I Xeroxed the correct solution and I slipped it inside the jacket with the DVD. So that if you get down to the end of the tape or the end of the DVD where that problem solution is, then you can actually look at that solution on a piece of paper there. Okay, so this is after the spring is activated. So what we had is a 60-degree incline with a kinetic coefficient of 0.4, and that cylinder coming down here had a friction force which was equal to mu k times the normal, and I think I worked that up. That's 0.4 coefficient times the normal force, which is 9.81 newtons. So that's the friction force. We have mg acting. Our normal force was here. mg was 2 times 9.81, and the incline angle was 60 degrees. Now, when the spring is activated, the spring is pushing at an ever-changing force against the object as the object is moving downward with some velocity. Right? And that spring force is what? K times its displacement that exists in the spring. So it's K, let's say it is a differential displacement dx. K dx. Now, that's the force, right? And so it is actually displaced by some amount. That's the spring force, and it's actually going through some displacement x as it moves. So let's see, can I get that on this picture? Let me erase that velocity expression. So here's where the spring was neutral, right at this point, and now the spring is acting from this point on. Okay? So if we look at that, if we look at now the work done, and we were addressing these problems using this energy principle in this fashion, so the left side of the equation must embody all of the work done by the active forces. So what we have there is the travel distance was 0.5 meters before it hits the spring. Down to where it hits the spring, and then x is the additional distance once the spring is active. So if we write our equation then, after the spring is active, we have these active forces that are in the direction of the motion made up of mu normal and k dx. So we have 0.5 plus some x, and that's going to be times the component of the weight minus the friction force. So it's going to be, I'll just go ahead and write the generalized term here. That's going to be mg sine of 60 degrees minus the 0.4 times 9.81 and then we then have to compute this work done by this term. Notice that the friction force, or mg sine 60 degrees is, here's your 60 degrees, mg sine 60 degrees is down the ramp in the direction of the motion, and so that's positive work done as it's traveling this plus this, and so I'm going to go ahead and show you that. And then this force is pointing back up, so that's the reason it's doing negative work. And then what you want to keep in mind then is that this thing is doing negative work as it travels through what distance? X. Through distance x. Okay. So what we have is we're subtracting then the energy due to this spring. And so this is going to be minus 1/2 k and we have to take and include x dx integrated from 0 to x. Starts here once the spring becomes active right here through some displacement x. And so that work term is negative then, and this is going to turn into an x squared over, well actually the half is actually embodied here. I should not have that there. Yeah. Because what I decided to do, instead of writing the just defined energy or the work done by the spring, which we derived previously was negative 1/2 k x squared, instead of just writing that down, what I decided to do is to write this down this way. So it's actually the integral of k kx dx from 0 to x. And that has to be equal to the change in the, what? Energy of the motion, which is 1/2 m times v2 squared minus v1 squared. And if we're going for delta maximum, which is what the question was asking, the maximum displacement, then what we're going to do is let the beginning velocity was 0. We're going to let the ending velocity, I'm going to go ahead and leave that in the equation for a moment. So we have then 1/2 m, and we had a 2 kilogram mass, I believe, times v2 squared. Is that all right? And your hand went up, Daniel. Was that because of me having the half and the? Good. I'm glad you caught that. Thanks. Okay. So now this term right in here was a number. I believe that turned out to be 13.07. So what we have then is a product up here, constant, half of the 13.07 plus a linear term. So let's just go ahead and tidy that up. So half of 13.07 was 6.535 plus 13.07x minus 1/2, and our stiffness on the spring was, I believe, 1,600 newtons per meter. Spring stiffness was 1,600 newtons per meter. And then we're going to get x squared over 2 there. Actually, the half is already pulled out here. So that becomes a quadratic term. That quadratic expression is equal to 1/2 times the 2 times the v2 squared. So I want to see if they can come in a little closer on that image there. Is that showing up on the screen okay for people? Yeah, I guess it is. Okay, good. So what I wanted to point out here, notice the 2's disappear over here on this side. So this is the square of the velocity during what portion of motion?
From the beginning until some time.
During the spring is active in compression, isn't it? And so this behavior is quadratic. This behavior is quadratic, is a function of the deflection of the spring. And then you take and smack a big old square root on that to obtain the velocity as the spring is displacing, as the spring is displacing. Question?
This equation starts when the bar hits the spring. It's going to have some initial velocity, so we can't set that equal to 0.
What I did right back here is I took it from when we began the experiment. And we began the experiment when the thing was at rest. And then we let the mass go. It slid 1/2 a meter plus the deflection in the spring. So this accounts for that motion, including the 1/2 a meter plus the deflection in the spring. Okay? So if we then just let that ending velocity go to 0, then this now becomes, x becomes delta max, doesn't it? So x equals delta max, the maximum deflection of the spring. If we clean this up, we have a quadratic equation that's minus 800 delta max squared plus the 13.07 delta max plus the 6.535 equals 0, and you just run a quadratic equation solver on that, or solve this graphically, and you find that delta max turns out to be 0.099 meters, or approximately 99 millimeters. Almost 1/10 of a meter. About this much. About 10 centimeters, right? All right? So that's a correction. what we did the other day, or what I did, I can partially blame you guys for not catching my mistake, yes, is I forgot to draw my free body diagram, and I didn't account for the energy that was, or the work that was done by that spring and actually causing that thing to slow down. And we were getting a result. Things were looking pretty screwy on the work that we had there. Something was obviously wrong. Okay, and we'd failed to draw that free body diagram with that spring force in there. Yeah.
So where are we accounting for the energy lost from the system due to friction?
Now that's built into the work done by this friction force throughout the entire travel distance. See, that's embodied right here in that negative term, negative work done.
While it's engaged with the spring.
Yeah, and they told us that that rod has friction all the way down, I guess even after the spring's activated.
So the amount of energy lost to friction would be that entire, the minus term multiplied by the entire x plus that. So that chunk is the end.
Over the entire travel distance, 0.5 plus the spring displacement. Yeah, good. That's the work that was done by that friction force. Good. Good.
A little hard to see broken up.
Okay. So it's important to keep your wits about you when you do these problems and try not to rush like I was doing and make sure you draw a good free body diagram so you don't lose one of these forces that's contributing. Okay. There was another question that was raised by Ian about this problem, and I'm not going to address it now. I might come back in the next class session and address it. Ian asked a question about this particular homework problem of the component of the P force, the force in this cable that is in the direction of the motion, asking if that was linear. And I said no, without explanation. So what I did is I actually went and did some calculations to see how that P component force varies as you move up along there, and I just don't want to take the time. I wrote it up, and it's not clean enough to put up here on the overhead right now, so I'll just come back at that with you. But that component of force that's doing the work that along the motion here, the P cosine of this angle right in here, that angle continues to change, and that P force that's contributing to the work done by P moving this object is not linear. Okay. So I'll try to clarify why in another class session. Okay. So let's go ahead and move on to this next section, and I think it would be worth looking. One more comment on that same section of homework. Here's another problem that's assigned, and I've written answers down here for you, and I don't know if you'll be able to read that on the overhead or not. Distance y let's see, distance s is the distance the 50 kilogram block travels. The distance 50 kilogram block here travels up the incline, and that distance s is 1.67 meters. The distance that this 15 kilogram cylinder travels is initially 1.2 meters while it has the additional 15 kilograms on it, and then that gets released right here at the support, and then that original 15 kilogram mass travels a total distance of 2.14 meters. 2.14 meters. Now, the word of caution I wanted to give you is that you need to work this problem in 2 steps. You can't take it from start to finish like I did that last problem. What you have to do is do the work energy problem with the combined 30 kilograms here and figure out what the velocity this system is traveling in right at this level. after this combined 30 kilograms has traveled 1.2 meters. You get those velocity figures, and then you start the problem over again without this extra 15 kilograms on there. That'll save you from some grief. You can't take it from start to finish. There's a reason for that. There's actually an energy loss in the system that we're not ready to talk about yet. There's an energy loss in the system when that 15 kilogram mass strikes this plate right here. Okay. And that will always occur in dynamics. If there's ever impact occurring, there's an energy loss in the system. So just keep that in the back of your mind. That'll be useful. All right. Now, one more thing in the next section now. I want to point out to you the transition we're making in the way that we're going to handle this is we're now going to define, as I did the other day, gravitational potential energy as the weight, mg, times a distance off of some reference datum. And in this case, here is a reference datum, and what they've done is they've defined this location in this picture as the reference datum where my finger is, and then they measure the distance against gravity that the object happens to be positioned at. So if it's above the datum, away from gravity, then that means it's got positive potential. That should be common sense to you. If you carry something up, you're storing energy into it, aren't you? If you carry something up to a higher elevation. Then, as I've said before, if you then release it, it starts giving up that potential energy, and it translates that potential energy into kinetic energy, energy of motion as it falls. Daniel?
Okay, so we're defining the zero of our coordinate axis at that line there next to the
Yes.
h equals 0.
Yep.
When the ball is above that and falling, is the work done on that ball by gravity negative or positive?
The work, okay, now you got to watch the phrasing there, okay? The work done by gravity, okay? mg is downward. That's a force downward, and if the object is coming back down, it's traveling in the same distance as mg, isn't it? Same direction as mg, so it's positive work done by gravity.
And that remains the same even after it passes below
Yeah, and if it goes below your datum, it's still, if it's still moving down, it's giving up that potential, and there's still positive work done by that. Now, we're not treating that, though, over on the left side of our equation. This term is going to sit on the right side, as I saw up there on the board. It's called delta VG, change in gravitational potential. And that'll be real clear, and it's actually quite easy to deal with if you write the equations the way that we're going to. You'll find it easier than treating it as the work done by gravity acting on the mass. Okay? One other thing that we're not going to focus on, if we were in Los Angeles where there's a large aerospace industry, or maybe up in Seattle with Boeing, we'd spend more time on high altitude types of configurations. And what happens here, without me spending time to derive it, is we set the gravitational potential at infinity. At infinity, deep space. So an object in deep space would have zero gravitational potential because there'd be no attractive, essentially the attractive force between the Earth and that mass in deep space is zero. So we define that as our datum out there at infinity. And then we let the object come closer into the gravitational field. And so without me going through the derivation, here's the defined where the radius of the Earth is capital R, and the distance from the center of the Earth to some altitude, capital R plus the altitude above the surface, that distance they call little r, and here's the defined potential. So the potential is negative because we've set the datum out at infinity. So if you do any if you do any high altitude kind of problems, just look this thing up. The derivation is right here without too much it's not too complex. I just don't want to take the time on it. Okay. The other piece is the next page, is the elastic potential. And remember when we did the work done to the spring by a force causing the spring to either extend or compress. When we did that, the work was negative. Okay? Now, if we move that information or that energy to the other side of our equation, it's going to become positive. And that becomes what we call the elastic potential. So the elastic potential is defined as, again, that kx dx integral for a linear spring, and it's going to be positive 1/2 kx squared, where x represents what?
The displacement.
The displacement from the undistorted spring length. Okay? From the undistorted spring length. And so what's going to happen is if you have a spring then at some position x2 and it previously was at position x1, then here's the change in elastic potential. It's that simple. It's 1/2 k times the difference of the squares of the displacements. So, we're now ready to work some problems. I think you'll like these. So let's tackle a problem. No friction on this one. We have a mass of 1/4 kilogram up here at position A, and we release it from rest, slides down the smooth guide, smooth wire. Where is it going fastest?
At the very bottom.
At the very bottom. It's given up all of its gravitational potential. It's given up all of its gravitational potential. It's going fastest there. And what direction it's going? Is it going down there?
Sideways.
To your left, right? It's heading to the left right there. So it's changed its direction from vertical to horizontal, and it's going its fastest right there. Now, what about the speed here versus here?
Can't quite see the hues.
Should be the same.
Okay, yeah, same speed.
Same speed.
Because it's the same
Speed
height.
down here, speed up over on the left. Right? You with me? Because what's happened? It's got a certain speed when it's coming down, finishing the straightaway, comes into the curve, and it's giving up still some more gravitational potential, still speeding up till it gets down here. And then it starts storing gravitational potential in, again, as it comes up here and slows back down some. So its speed here was the same as the speed is over here. Then it's going to go up. They want us to take it on up 45 degrees here to this final position, and they were asking us to figure out not the speed, but we can figure that out pretty easily. They want us to figure out the force between the wire and the bead as it passes this point. So that means there's a transverse force there, a transverse force exerted by the wire against the bead. Okay. I wrote the answer down out of the solution manual, 14.42 newtons, if that doesn't show up on the recording. Is there any work done?